Hello there, and welcome to Science for Sleep, where curiosity gets cozy and quantum mechanics wears pajamas. Tonight's little journey is a soft dive into one of the strangest truths in science, a truth so peculiar that even the people who discovered it have said, if you think you understand it, you probably don't. Quantum physics, where particles are waves and waves are particles, where things can be in two places at once, and where cause and effect sometimes feel like they're just politely taking turns. It's a world that doesn't quite make sense, and yet somehow everything still works. Your body, your phone, the stars, they all run on rules that don't even agree with themselves. But before we float too far into the uncertainty, let me ask, where are you listening from tonight? What time is it in your little pocket of the cosmos? Because here we are, you and I, sharing a moment that technically might not exist. A moment made of sound waves and sleepy wonder, and probably just a bit of borrowed Wi-Fi. If you find this sort of odd comfort soothing, or if it gently untangles your thoughts at the end of a long day, I'd be ever so grateful if you gave the video a like, or maybe subscribed, so that this little patch of calm can find others who need it too. Now, I do hope this isn't so fascinating that it keeps you awake, but if it is, well, at least it's the strangeness of the universe keeping you company. So settle in, slow your thoughts, and let's begin. Because somewhere between probability and poetry, particles and possibility, lies the story of how nothing makes sense, but everything works. Have you ever walked into a room and forgotten why you were there? Or had a dream that felt so vivid, so achingly real, that waking up felt like the illusion? These little glitches in experience may seem trivial, but they point towards something quietly extraordinary. Our minds don't just observe reality, they interpret it, and sometimes what they create feels more solid than the world itself. Quantum physics, for all its equations and lab coats, doesn't begin with math, it begins with perception. Because what we call reality, the table under your teacup, the moon outside your window, the soft rhythm of your breath, is filtered through a mind that assumes things should be consistent. And in many ways, they are. Until, of course, they aren't. Consider this. You look at a candle. The flame flickers. You know it's fire. But on a quantum level, that flame is built from photons, packets of light that behave like particles one moment and like waves the next. It isn't just a poetic idea. It is a proven, repeated, impossible truth. The universe changes depending on how we look at it. The double-slit experiment is the classic example. If you've heard of it, you already know where this is going. If not, imagine this. You fire particles, let's say electrons, at a wall with two tiny slits. Behind the slits is a screen to catch them. You expect to see two neat piles of electrons, one behind each slit. But instead, you see an interference pattern, the kind you'd expect from waves going through both slits, overlapping, interfering. But here's the part that makes physicists rub their eyes and reach for tea. If you put a detector at the slits, to see which slit each electron goes through, the pattern disappears. Suddenly the electrons act like particles again. It's as if the universe notices you're watching and politely changes behavior. Now, that might sound like magic or madness, but it's neither. It's just quantum physics, a field where particles can be entangled across galaxies, affecting one another instantaneously, where a particle doesn't have a definite location or momentum until it's measured, and where possibilities exist in a strange soup of maybes until someone comes along and collapses them into one outcome. This is not just a scientific oddity, it's a mirror held up to our own minds, because in many ways we live in a constant wave function of perception. Think about memory. It changes every time we recall it. Think about decisions. They exist in potential, in parallel timelines of what if I had, until we choose. Our brains too collapse uncertainty into meaning, and maybe, just maybe, reality does the same. None of this is to say that physics proves consciousness creates the universe, but it does show us that reality is far less rigid than we once believed, and if the universe is soft around the edges, then maybe our perception is not a flaw in the system, but a feature of it. So here you are, listening, drifting, your body still, your breath steady, and somewhere inside your skull, 100 billion neurons are dancing in electric fields and chemical whispers, telling the story of what is happening right now. But if you really stop, if you really listen, what exactly is now? Quantum physics doesn't define the present as clearly as you might think, because in the smallest scales, time itself gets blurry. Events don't have a strict order. Cause and effect can blur. And yet, here you are, a living paradox. You exist. You are aware. And that awareness stitches the world together into something whole. Something that, however strange, somehow works. We often say that dreams feel real, but maybe it's more honest to say that reality feels dreamlike. Not because it isn't solid, but because the foundation beneath it is anything but. Particles that can be in two places at once, objects that spin both clockwise and counterclockwise, and perhaps the strangest part. When you look away, the math says the universe doesn't settle on one outcome, it holds its breath, it waits. Not for you exactly, but for a measurement, for a moment, for something definite to emerge from the cloud of possibility. It is hard to wrap a sleepy mind around. But then again, that's the beauty of it. You're not expected to solve this tonight. You're only asked to wonder, and as your thoughts begin to drift, perhaps a part of you feels it. That quantum strangeness isn't just about electrons or laboratories. It's about experience, about being, about the quiet miracle of things not making sense, but working anyway. We don't live in equations, we live in sensations, in perception. In a world filtered through the stories our brains whisper to themselves when the lights go out. And yet, quantum physics seems to suggest that reality itself may do something similar. That the building blocks of the universe don't come with fixed labels or instructions, only probabilities, only tendencies, until something happens to make a choice. Take quantum superposition. It tells us that particles can exist in multiple states at once, not as a metaphor, not as a confusion, but as a physical truth. A single electron can be in more than one place at the same time. A single atom can spin in opposite directions, not either or but both, until measured, until interacted with, until something decides. That sounds impossible. It feels wrong. But then again, the world doesn't ask us to agree. It simply continues to function. And maybe that's the strangest part, that we're held together by laws that seem too surreal to be real. And yet here you are, breathing, dreaming perhaps. When Erwin Schrödinger introduced his now famous cat in a box, simultaneously dead and alive until observed, he wasn't celebrating the absurd. He was showing us how absurd quantum theory seemed, even to its creators. But the deeper message wasn't about the cat, it was about us, and what it means to observe. Observation in quantum mechanics isn't just about seeing, it's about interaction, about entanglement, about becoming part of the thing you measure. When we try to separate ourselves from the system, to be neutral outside observers, we change it anyway. Because in the quantum world, there is no outside. The act of looking becomes part of the equation. And isn't that a little like being human? We walk into rooms and change their atmosphere. We remember things differently just by recalling them. We influence one another without even speaking. Our presence changes the story. And maybe the universe too is telling a story, not with words, but with waves and particles and fields, with clouds of possibility. You can imagine it like a symphony that doesn't settle on a final note until someone leans in to listen, or a book that writes itself only as it's read. Quantum mechanics doesn't offer us a clear picture. It offers us many pictures, some contradictory, some incomplete, all true in different ways. And that too feels familiar, because people are like that. You can hold love and fear at the same time, joy and sorrow. You can be certain and unsure in the same breath. So maybe quantum physics isn't just about atoms. Maybe it's also about empathy, about holding multiple truths at once and letting go of the need for any one of them to be final. In this world, contradictions don't always cancel. Sometimes they harmonize. So as your mind begins to float a little, as your thoughts loosen from the tight knots of the day, know that this too is quantum in nature, a gentle uncertainty, a moment between moments, a question without a fixed answer. And yet, it works. It always has. In dreams, in music, in sleep. The world does not always need to make sense to make beauty, or meaning, or peace, and maybe that's all right. Long before anyone spoke of wave functions or Planck constants, before electrons had orbits or Schrödinger boxed up his unfortunate cat, human beings looked up at the night sky and asked the same silent question. What is this made of? The answers were stories, not equations. The ancient Greeks imagined everything was composed of 4 elements: earth, water, air, and fire. It was elegant, intuitive, and wrong. But still, it tried to make sense of a strange world where lightning could fall from the sky, and stones could be ground into powders, and powders could vanish into flame. In India, the Vedic texts spoke of indivisible atoms long before microscopes or particle accelerators. The Jain philosophers proposed that these smallest bits of matter carried not just substance, but also motion and soul. In China, Taoist alchemists saw matter as an ever-changing interplay of yin and yang, a dance of opposites, a transformation that never ceased, much like the uncertainties that modern physics would one day discover. But no matter the culture, no matter the language, there was an instinct to peer beneath the surface, to search for hidden patterns, to believe that what looked solid and predictable might at its heart be fluid and strange. That instinct never left us, it only changed names. Fast forward to the 17th century. Isaac Newton gave us a clockwork universe, orderly, predictable, a cosmos that ran on forces and masses, a kind of divine machinery where everything obeyed rules, and for a time, that seemed enough. Planets orbited with calculable grace, apples fell, time ticked forward, and light, mysterious as it was, seemed to behave like waves. Until the 1800s, when physicists started to notice something odd about that light. They tried to model it as a wave, and it worked, up to a point. But when they looked more closely, when they observed how metals emitted energy when heated, the math broke down. At high frequencies, the predictions shot to infinity, which scientifically speaking is not ideal. This became known as the ultraviolet catastrophe, and it was a quiet sign that the universe was not going to be explained so easily. Enter Max Planck. In 1900, he offered a fix. Energy, he said, must come in discrete chunks, little packets, quanta. He didn't set out to revolutionize physics. He just wanted the equations to behave. But what he started would open the door to a reality where particles are waves, where observation creates change, and where certainty itself begins to dissolve. Then came Einstein, 1905. He suggested that light wasn't just a wave, but also a stream of particles, photons. Light in his hands became something dual, both and. A paradox with an elegant name, wave-particle duality. And soon, the floodgates opened. Niels Bohr offered a model of the atom that defied classical mechanics. Electrons didn't spiral in, they jumped. They occupied discrete energy levels, and they changed those levels not gradually but instantly. It was beautiful and bizarre. Then came Werner Heisenberg, who told us that there are things we cannot know at once, position and momentum. The more you know of one, the less you can know of the other, not due to instruments, but to nature itself. Uncertainty was not a flaw. It was fundamental. Erwin Schrödinger gave us the wave function, a mathematical description of a particle not as a dot, but as a cloud of possibilities. And suddenly, reality wasn't a point on a line, but a smear of maybes. Measurement collapsed that smear into something concrete. But between those measurements, only probability, only potential. In a sense, history became a story of moving from certainty to softness, from hard truths to flexible frameworks. And yet all along cultures had already imagined a world like this. The Aboriginal dream time, where time and space are not linear but layered. A place where myth and matter intertwine and the observer is always part of the story. The Zen koan that defies logic to awaken something deeper than reason. The hermetic texts of old that whispered as above, so below, as if hinting at entanglement centuries before it had a name. Perhaps that is the great echo, that quantum physics, in all its precision, began by walking into mysteries our ancestors had already sensed. The difference was not curiosity, it was measurement, a microscope instead of a myth, a spectrometer in place of a sacred rite. But the awe remains the same, to look closely at matter and find not answers, but questions, not bricks, but fog, not edges, but entanglement. And if the universe is strange now, perhaps it's only because we've finally learned to listen to the strangeness that was always there, waiting. As quantum physics grew up, it did not become less strange, it became more so. By the mid-20th century, the theory had matured into what is now called quantum mechanics, and with it came a new set of ideas that danced even further from common sense and ever closer to something mythic. Quantum entanglement, a word that sounds almost poetic. Two particles, once linked, remain connected no matter how far apart. Measure one, and you instantly know the state of the other, even if it's across the galaxy. Einstein called this spooky action at a distance. He was skeptical. He didn't like the idea that information could travel faster than light, or that reality could be so deeply stitched together. But over time, the experiments piled up, and the results were clear. Entanglement was not a trick, it was real. And so the universe, once thought to be a giant clock, suddenly felt more like a web, not distant parts, but one vast field of relationships, which, oddly enough, is not so different from how many ancient cultures saw the world. Indigenous cosmologies often describe nature as a single living system. Rocks, rivers, trees, sky, and people all part of the same breathing body. Quantum physics, though born from measurements and mathematics, arrived at something similar. The idea that you cannot fully separate anything from anything else. In the Western tradition, the mind and the world were often split. Subject and object, observer and observed. But in quantum mechanics, the line blurs. When you observe something, you are part of it. You change it. This led to fierce debates. Bohr versus Einstein. Measurement versus reality. Does the moon exist if no one is looking at it? Is the universe fundamentally indeterminate, or is there some hidden variable underneath it all keeping the books tidy? The arguments were not just technical, they were philosophical. They touched on consciousness, cause, and the very idea of what it means to know. And meanwhile, outside the labs, cultures continued to echo these questions in their own ways. In Japanese Shinto belief, the spirit world and the material world are not separated. A stone may carry presence, a tree may hold memory. In African spiritual systems, what we call the physical and the metaphysical are not two categories, but one flowing reality. And quantum mechanics, for all its complexity, suggests something eerily close, that what we call matter is not solid, but a dance of interactions. That observation is not passive, but participatory, and that everything, even the empty spaces, is alive with potential. It's tempting to say science has finally caught up with ancient wisdom, but perhaps it's more humble to say we're circling the same fire from different directions, because the questions remain, not just what is it made of, but what does it mean? Quantum theory doesn't answer that, but it does invite us to ask it more carefully. In the Sufi tradition, truth is something tasted, not dissected. It is known through poetry, through paradox, through love. In some Native American languages, verbs dominate over nouns. The world is described not as things, but as events, as movement, as becoming. And quantum physics might agree. Electrons are not static. They are tendencies, patterns, likely places to be. Reality, at its base, may not be a set of things, but a shifting field of interactions, a process, more verb than noun. So what does this tell us? It tells us that our way of understanding the world has always been a blend of measurement and metaphor, of math and myth. The Higgs field, which gives particles their mass, is not so different in spirit from the idea of a sacred field through which all being is connected. Both are invisible, both are necessary, both describe something we can only glimpse through effects, never directly. And maybe that is what history teaches us. Not just what we used to believe, but that belief itself is a creative act. From fire gods to field equations, from sacred smoke to superposition, humans have always tried to make sense of the unreasonable success of the universe. And along the way, something emerges, a kind of humility, a reverence for what we do not yet understand. Quantum physics is not a conclusion, it is a beginning, a reminder that the more closely we look, the more strange and wondrous everything becomes, and that perhaps in every age we're just barely learning how to see. Quantum physics does not explain the world the way we might hope. It does not hand us answers in clean envelopes. Instead, it invites us into a dance, a slow, strange waltz with uncertainty. But to understand what it does say, we have to start with what it is. Quantum mechanics is the study of the smallest things, the particles that make up atoms and the forces that guide them. It describes a world that is invisible to the naked eye, yet underpins everything you can see, hear, touch, and imagine. At this scale, particles don't behave like marbles or billiard balls. They are not solid in the way we think of solidity. They behave more like waves, and more like information, and often like something in between. The most basic idea, that particles don't have fixed properties until we measure them. Imagine you're trying to find an electron. You expect it to be somewhere, and yet, until you look, the electron isn't in a single place. Instead, it exists as a probability cloud, a wave function, telling you where it might be, not where it is. And when you finally measure it, the wave function collapses, and the particle chooses a position. This is not just a trick of ignorance. It's not that we don't know. It's that nature itself is undecided until a measurement is made. This is the heart of the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. It suggests that quantum systems don't have definite properties until those properties are observed. That reality is fundamentally probabilistic. Other interpretations disagree. Some say the particle always has a position, and we just don't know it yet. Others, like the many worlds interpretation, say that every possible outcome happens in a branching multiverse, and measurement is just how we find ourselves in one thread of that cosmic braid. Still, the math works, and it works astonishingly well. Quantum theory makes predictions that have been tested to absurd degrees of accuracy. Some experiments confirm its equations to more than 10 decimal places. So what are the tools of this theory? There are a few fundamental principles that guide it. 1. Superposition. A particle can exist in multiple states at once. Until measured, an electron can be here and there. It isn't in between, it's in both. 2. Entanglement. Two or more particles can become linked such that the state of one instantly affects the state of another, no matter the distance between them. Measure one, and the other knows what to do. 3. Uncertainty. Heisenberg's principle tells us that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The more you know of one, the fuzzier the other becomes. 4. Quantization. Some properties, like energy, come in discrete amounts, not smooth flows, but jumps between fixed levels. Let's take a moment with each. Superposition is often misunderstood, but at its core it means that before you measure a system, it exists in a combination of all possible outcomes. Like a coin spinning in the air, except the quantum coin is in a blend of heads and tails, and it only chooses when it hits the ground, or when someone looks. Entanglement, on the other hand, shakes our sense of separation. It tells us that the universe is connected in ways that go beyond space and time. You can create a pair of particles in such a way that they share a quantum state, separate them by a few feet or by 1,000,000 light years. Measure one and the other responds, instantly. This is not information travelling faster than light. It's something deeper, a correlation born at the moment of creation. Einstein didn't like it. He called it spooky, but even he admitted the math didn't lie. Then there's uncertainty. At the smallest scales, nature becomes a bit imprecise. This doesn't mean it's sloppy. It means it is governed by limits, built-in boundaries that keep certain knowledge forever just out of reach. You can know exactly where a particle is, but then you won't know how fast it's going, or you can measure its speed precisely and lose track of where it is. This principle isn't a bug, it's a rule. And finally, quantization. The idea that energy comes in chunks. Think of a staircase instead of a ramp. Electrons don't slide between energy levels, they leap. They jump from step to step, and those jumps emit or absorb very specific amounts of energy, often as light. This explains why atoms emit light in discrete colours, why neon signs glow red, why sodium burns yellow. Every jump has a signature, a fingerprint of energy, and it is from these fingerprints that we began to build the quantum world. Each of these ideas on their own is strange, but together they form a framework that describes reality more accurately than anything that came before. They power semiconductors, which power computers, which power the screen you're reading this on. They describe the chemistry that shapes molecules, the reactions that let stars shine. They even underlie technologies like lasers, MRI machines, and quantum encryption. Quantum physics isn't just a theory. It is the scaffolding of modern life, and yet, we still don't fully understand it. We can write the equations, we can run the experiments, but when we ask what is actually happening, the answer is softer, more poetic, more elusive. It is as though the universe has given us perfect predictions without a full explanation, as though nature says, you may use it, but you may not know why. And so we do. We build, we learn, we marvel, and we wonder. Because even now, with all we know, quantum physics remains the most successful, confounding, and beautiful mystery we have ever touched. Let us float deeper now, beyond the textbook definitions, into the weird warmth of quantum intuition. Because what begins as equations soon unfolds into paradoxes, into puzzles that resist simple answers. And one of the most curious puzzles is this: what counts as a measurement? In quantum physics, measurement causes change. It takes a blur of possibility and collapses it into a single reality. But what does it mean to measure something? Does it require a conscious observer, a machine, a tree falling in a forest? The question remains open, and it leads to deeper mysteries. Because if the universe doesn't settle into a definite state until something interacts with it, then when did it first collapse? At the Big Bang? At the rise of life? Or does it collapse continuously, with every new relationship, every new ripple? Physicists have proposed answers. Some say it's the act of decoherence, when quantum systems interact with the environment in such a way that their wave functions no longer interfere. In this view, measurement isn't mystical, it's statistical. It happens constantly, everywhere, as systems bump and blend and blur into classical outcomes. Others keep the mystery alive. They ask whether consciousness itself plays a role in collapse. This is not the dominant view, but it's not without weight. Some interpretations, like those of Eugene Wigner and John von Neumann, wondered whether mind and matter are more deeply linked than we understand. That the observer isn't just an outsider but an ingredient. Of course, most working physicists set these questions gently to the side. They focus on predictions, on calculations, on results, and who can blame them? Quantum mechanics delivers answers whether we understand the question or not, but still, the question lingers. What is reality when no one is looking? Maybe it's like the moon Einstein joked about. I like to think the moon is there even if I am not looking at it. And maybe it is. Or maybe it isn't. Another paradox, the quantum Zeno effect. A strange twist where constant observation can freeze a system in its state. If you watch a particle closely enough, you can prevent it from changing. Not because you hold it, but because you keep measuring. It's like a pot that really won't boil if you keep watching it, but for quantum reasons. This shows how even the frequency of measurement can affect the evolution of a system. And this gives rise to a new idea, that the universe isn't just a set of things, but a choreography. Everything depends on interaction, on context, on relationship. Particles don't have identities apart from how they interact with others. They don't have colour or spin or charge except in relation to other particles and the fields that cradle them. So maybe the world isn't made of stuff, but of stories, of interactions, of exchanges that build a reality one quantum tick at a time. Another marvel, virtual particles. Particles that blink in and out of existence in the vacuum. Not stable, not permanent, but fleeting disturbances in a field. These particles may exist for only a moment, but they shape everything. They shift the energy of space. They influence atomic behaviour. They are part of the quantum foam that buzzes beneath what we call empty. Even nothing in quantum physics is not truly empty. It teems, it ripples, it seethes with borrowed energy and brief lives that leave real effects. This is how forces arise, as interactions between particles mediated by other particles, some real, some virtual. Photons carry the electromagnetic force. Gluons hold quarks together in the atomic nucleus. W and Z bosons govern the weak nuclear force, and the Higgs boson is tied to mass itself. Each one is part of a vast quantum field, and those fields, they are not confined to particles. They stretch across space, of which every point is a possibility, a stage on which existence performs. In this framework, the universe is not made of things. It is made of fields. Particles are just excitations, local hiccups in a deeper medium. You're not made of particles, strictly speaking. You're made of fields in a temporary state of focus. And somehow this all holds together long enough for you to hear these words, for you to rest in your body, and to wonder what holds it all together. Quantum theory says fields do, probability does, measurement does, and yet we don't fall through the floor. The atoms in your skin resist the atoms in your chair, because the wave functions of electrons have a rule. No two can occupy the same state in the same place. This is the Pauli exclusion principle. It sounds obscure, but it's the reason your tea doesn't spill through your mug. Quantum rules shape macroscopic order, and without them, solidity would be a myth. And still there is more. Bell's theorem, a stunning result from the 1960s. John Bell devised a way to test whether the universe obeys hidden variables or whether it truly embraces non-locality. Experiments followed, one after another. They closed loopholes. They tested entangled photons and electrons and atoms, and every time they came to the same conclusion: reality is not local. What happens here can depend on what happens there. Quantum theory was right. Einstein was not. And still the moon glows. Still the tide rolls in. None of this changes your morning tea or your memory of childhood, but it changes what lies beneath. And what lies beneath is not a foundation of bricks, but of breath. The breath of a universe that does not always declare itself, but waits just a little to be known. And still we drift, deeper into the currents of what quantum physics tells us. Not just about particles, but about patterns. not just about mechanics, but about mystery. Because for all the precision of quantum equations, their implications are wide open, not only for what they describe, but for what they suggest. They suggest a universe that is not made of things, but of tendencies, of maybes, of flickers, a cosmos whose fabric does not wait to be seen, but is woven by the act of seeing. One of the frameworks that deepens this picture is called quantum field theory, or QFT. It blends special relativity with quantum mechanics, uniting the strange and the swift into a single stunning system. Here, particles are excitations of underlying fields, and every field pervades all of space. There is an electron field, a photon field, a Higgs field, and what we call a particle is simply a little ripple, a vibration in that universal medium. Like a note plucked from silence, or a whisper in the fabric of the void. Every interaction, every force, every structure you can name emerges from how these fields bump, intertwine, and echo through the quantum sea. This model is incredibly successful. It gave rise to what we now call the Standard Model of Particle Physics, a catalogue of known particles and forces that so far accurately describes everything we've measured. It predicted the existence of the Higgs boson, and in 2012 we found it, at the Large Hadron Collider in Geneva, where protons are hurled into each other at nearly the speed of a light. The Higgs emerged, not directly, but through its fingerprint, through the particles it left behind as it vanished back into silence. And yet, even this monumental theory is not complete. It doesn't include gravity. It doesn't explain dark matter or dark energy or why the constants of nature are what they are. It works, but it whispers of something more, which brings us to quantum gravity, a field still under construction. Physicists seek a theory that merges quantum mechanics with general relativity, Einstein's grand vision of gravity as the curvature of space-time. But the marriage is not easy. General relativity is smooth. Quantum physics is grainy. Trying to stitch them together is like trying to fit sand into silk. Some propose string theory, the idea that particles are not points, but tiny vibrating strings whose harmonies give rise to mass, charge, spin. Others explore loop quantum gravity, which reimagines space-time itself as woven from quantum threads. Still others look to emergent gravity, or entropic models, where gravity is not a force but a side effect of information itself. Information. That strange modern heir to both energy and matter. Some say that everything can be described as information, that the universe is not a machine, but a computation, and that quantum mechanics is the operating system running just behind the scenes. In this vision, reality is encoded in qubits, not atoms, and our universe may be more like a hologram than a place, a projection of information from a deeper dimension. Again, this is not science fiction. These are real, testable ideas being debated in real laboratories. They haven't replaced the standard model, but they press against its walls. They say, there is more, and even if you never solve these equations, even if you never read a Lagrangian or balance a Feynman diagram, you are still part of this story, because your body obeys these laws. Your thoughts are quantum processes. Your every breath, every blink, every moment of wonder is shaped by a physics that is stranger than we dreamed, and perhaps more intimate than we imagined. So when you think of the quantum world, don't just think of particles in boxes or cats in paradoxes. Think of ripples. Think of relationships. Think of the quiet truth that nothing is truly isolated, that to exist is to participate, to entangle, to be here, even briefly, in a cosmos that runs not just on logic, but on potential. And that potential, though uncertain, is never empty. It is humming. It is waiting. It is you. Let us step now into the heart of the strange, because if quantum physics is already a riddle, its details are where the wonder begins to bloom. This is the deep end, the inner chambers of the puzzle, where even the laws of reality begin to tremble, and we begin, perhaps fittingly, with something that sounds simple: quantum tunneling. Imagine you roll a ball up a hill. If it doesn't have enough energy, it rolls back down. Makes sense. Classical sense. But in the quantum world, a particle might just appear on the other side. It has not rolled over. It has not climbed. It has tunneled through the barrier like a ghost slipping through a wall. Why? Because in quantum mechanics, there is always a non-zero probability that a particle can be where it should not be. It doesn't break the rules. It just gently refuses to obey them strictly. This is not rare. It is not obscure. It is the very reason the sun shines. Inside stars, nuclear fusion requires particles to overcome enormous energy barriers. But thanks to quantum tunneling, they don't need to leap the whole wall. They just need to have a chance of tunneling through. And so they do. And stars burn. And we exist. That's one flavour of impossibility. Here's another: quantum teleportation. Now, this isn't the beaming up kind. You can't teleport matter, but you can teleport information. The exact quantum state of a particle can be transferred to another particle at a distance, using entanglement and classical communication. The original state is destroyed, but recreated elsewhere. And no, this does not violate the speed of light, because entanglement alone can't transmit data. You still need a classical message to complete the link, but still, it means that quantum identity can leap, can skip across space, if not with feet, then with logic. This is more than a trick. It's the basis of quantum communication and quantum computing. Which leads us to the quantum bit, the qubit. In a classical computer, a bit is either 0 or 1, like a switch, on or off. In a quantum computer, a qubit can be 0, 1, or both at once. Thanks to superposition, a qubit exists in a blend of states, and when you string multiple qubits together, the system doesn't just scale, it expands exponentially. 2 qubits can hold 4 states, 3 can hold 8, 10 can hold over 1,000. This gives quantum computers an ability to process information in a way that is not faster, but fundamentally different. They explore many paths at once. They solve problems not by brute force, but by riding probability like a river. They're not here to replace your laptop. But for certain tasks, like factoring huge numbers, simulating molecules, searching massive data spaces, they could outshine anything we've ever built. Quantum computing is still young. It faces challenges: decoherence, error correction, scalability. But it's no longer theory, it's real, it's happening, and behind it all is that quiet, consistent principle that reality itself is not binary, it is layered, fuzzy, poised between options until nudged. And there are more nudges to explore. Take vacuum fluctuations. In quantum field theory, empty space is never truly empty. Even in a perfect vacuum, particles flicker into existence and then vanish again. These virtual particles can affect the real world. One famous example, the Casimir effect. Place 2 uncharged metal plates very close together in a vacuum and they will attract each other. Why? Because the quantum fluctuations between them are different from the ones outside them. Space itself has pressure, not from air but from uncertainty. Reality, when left to itself, still hums. This hum becomes meaningful in the early universe. Quantum fluctuations, tiny variations in energy, were amplified by cosmic inflation and became the seeds for galaxies. All structure, all stars, all life emerge from quantum noise. So when we say, everything came from nothing, this is what we mean. Not emptiness, but potential. Not silence, but a song we are still learning to hear. Next, we venture into something darker, literally, black holes. These are regions of space where gravity is so strong not even light can escape. According to general relativity, they should be permanent, devouring anything that crosses their edge. But quantum physics disagrees. Stephen Hawking showed that black holes are not entirely black. They radiate. They glow, very faintly via a process now called Hawking radiation. This radiation arises from quantum effects near the event horizon, where virtual particles become real and one falls in while the other escapes. Over time, a black hole can evaporate. This leads to the black hole information paradox. If a black hole can vanish, what happens to the information it swallowed? Quantum theory says information must be preserved, always. But if it falls into a black hole, then where does it go? Does it leak out with the radiation? Does it stay behind in the remnants? Or is it somehow smeared across the horizon, like a cosmic tattoo? These questions remain open. They dance at the edge of what we know, and yet they are not just abstract. They are about the coherence of the universe, about whether we can trust the rules that govern it. So far, quantum mechanics has never failed, and yet it keeps us guessing. It brings us to answers that end in more questions, to certainty that feels like possibility, to a world that burns with logic but flickers with paradox. And in that flicker, we find the deep beauty of not quite knowing, of almost knowing, of maybe understanding just enough to fall asleep under the stars and dream of particles we cannot see. So much of quantum physics happens in places we can't quite go, not yet. But sometimes strange quantum truths touch the surface of our everyday world, not as theories, but as technologies. Consider the transistor, the building block of every computer. It exists because of quantum tunneling, because electrons can move through barriers not by pushing past them, but by ghosting through. Your phone, your microwave, your GPS all rely on the rules of the subatomic. Even time itself, as measured by atomic clocks, is shaped by quantum transitions. Electrons jumping between energy levels in cesium atoms, marking seconds with a rhythm so precise it would take millions of years to drift by even one. These clocks guide GPS satellites. They keep our networks in sync. They structure our days, all of it from particles too small to see. But maybe we feel their touch anyway, because quantum effects are not just mathematical, they are experiential. They live in the silence between thoughts, in the flicker of a half-formed idea, in that moment when you walk into a room and forget why you came. Is that quantum? No. But it is uncertainty, it is potential, and it feels familiar. That strange space between what is and what might be. Now let us move to coherence, not in sound, but in quantum states. Quantum coherence is the ability of a system to remain in superposition. It is delicate, fleeting. Anything from heat to noise to cosmic rays can cause decoherence, collapsing the state into something definite. This is the great challenge of quantum computing, to preserve coherence long enough to compute, to hold the wave without crashing it. The longer you can keep the system in this suspended maybe state, the more power you have. Not brute force, but elegance. Some systems achieve this by cooling to near absolute zero. Others by shielding, by clever encoding, by error correction that catches mistakes before they spread. It is not easy, but it is happening, and every advancement brings us closer to something new. A machine that thinks in maybes, that sees all paths at once, a way to simulate reality not step by step but all at once, like a chord instead of a scale. That is what quantum computing promises, a shift in how we understand problems, and from that, perhaps a shift in how we understand ourselves, because we too live in superposition. We too collapse into choices, and maybe, just maybe, we too can learn to hold the tension between options without rushing to resolve it. There is poetry in that, and physics. Now let us touch something equally strange. Quantum biology. Yes, biology. Because life might not ignore the quantum, it might use it. Consider photosynthesis. Plants absorb sunlight and convert it to energy. This process is remarkably efficient. and some studies suggest that quantum coherence might help guide the energy through the molecular maze within the cell. Not randomly, but precisely, as though the energy explores all paths at once and chooses the best. Like a quantum algorithm inside a leaf. Or take bird navigation. Certain migratory birds appear to use quantum entanglement in their eyes to detect the Earth's magnetic field. This is not proven, but the evidence builds. And if true, it means that biology has found a way to keep coherence alive inside warm, wet tissue. That life has learned to whisper to the quantum world and hear its reply. We do not yet know the full story, but the possibility opens something beautiful. That evolution did not bypass quantum weirdness. It embraced it. And maybe, tucked inside our own cells, are echoes of that same whisper. Next, let us touch a dream, quantum consciousness. A controversial idea, an uncertain one, but a question worth holding. Could consciousness arise from quantum processes in the brain? Some say yes. That microtubules, tiny structures inside neurons, may host quantum computations, that the brain is not just electrical, but quantum mechanical. Theories like OR, proposed by Roger Penrose and Stuart Hameroff, explore this idea. They are speculative, they are debated, but they keep a door open, a door between physics and the mind. And even if consciousness doesn't rely on quantum tricks, there is still a resonance. The brain, like a quantum system, processes uncertainty. It predicts. It collapses waves of possible futures into action. It dreams. It wonders. It lives in ambiguity and makes meaning anyway. So maybe the question isn't, is the brain quantum? Maybe the question is, why does the quantum feel so much like us? Not because we shaped it, but because we were shaped by it. We are not outside this strange machinery. We are made of it. Our thoughts, our questions, our ability to love and to lose, to imagine, are all born from rules that were never meant to be understood. And yet, here we are, trying. We end this deeper dive with questions, because in quantum physics, answers often lead straight to the next doorway. Let us pause with one of the strangest questions yet. What is a measurement? We've said that observation collapses the wave function, but what if we could delay that observation? What if we decide how to measure after the particle has already passed through the experiment? This is the idea behind Wheeler's delayed choice experiment. Imagine light travelling through a device. If you look one way, it behaves like a particle. If you look another, like a wave. But if you wait to choose after the light has passed the critical point, it still behaves as if your later decision reached backward in time and changed its nature. How can this be? It seems absurd. It seems impossible. And yet the experiment has been done, repeatedly, and the result is always the same. Quantum systems respond not just to what we do, but to what we might do. The universe, it seems, knew your question before you asked it. This bends our idea of time, of cause and effect, and leads to the even wilder domain of quantum retrocausality. The possibility that effects might ripple backward, that the future could nudge the past. No, this doesn't mean we can send messages to ourselves in history. It doesn't mean paradoxes are real. But it does mean the boundaries between past and present, choice and outcome, might not be as rigid as they seem. This aligns in a strange way with something else, Feynman's path integrals. Richard Feynman proposed that a particle doesn't just take one path from point A to point B, it takes all possible paths, every route, every curve, even paths that loop, that double back, that make no classical sense. And somehow, from this infinite garden of possibilities, a single path emerges as the observed outcome. But it only emerges after the math is done, after interference has cancelled out the others. This is how quantum systems behave, not like runners following a track, but like dancers exploring every step before settling into rhythm. The path we observe is not the only one that mattered. It is the one that survived the dance, and maybe so are we. This idea extends beyond physics. It begins to shape how we see decision and memory and meaning. What if the story you're living was once one of many? What if your present is just one strand woven from a superposition of possible pasts? And every moment, every act of attention is a kind of measurement? This brings us back to the quantum mind, not as a claim, but as a metaphor. That we too explore many paths, that we too collapse into being with each breath, each choice, each act of awareness. So when you feel uncertain, when you wonder which way to go, remember, that uncertainty isn't the opposite of truth. It is the field from which truth emerges, a wave becoming a word, a breath becoming a vow. And here, toward the edge of what physics can say, sits one last marvel, the observer effect. A particle behaves differently when it is measured. But what does that mean, really? Does the particle know? Of course not. Particles do not think. But the system as a whole responds. To measure is to change. To notice is to shape. And that may be quantum physics' deepest whisper, that presence is power. That to witness something is to become part of it. So look closely, not just at experiments but at life, at the spaces between people, the silences between words, the breath before you speak. That too is a kind of wave function, and your attention is the measurement that gives it shape, not forcefully, not finally, but gently, like a photon kissing an atom and turning possibility into form. So in the end, what is quantum physics? It is math, an experiment, and precision. But it is also mystery, and metaphor, and mirror. It reflects back our deep truth, that to live is to exist in between, to move through uncertainty with grace, to make choices not knowing all the outcomes, to be even briefly like light, not just a point, but a wave. Not just one thing, but a field of infinite paths collapsing softly into now. To truly grasp where quantum physics came from, we have to look back, not just to experiments and equations, but to the slow unfolding of questions humanity has asked for millennia. Quantum mechanics didn't arrive fully formed. It emerged from centuries of wondering, of pushing against the boundaries of what could be known, of puzzling over light and matter and the invisible machinery of the cosmos. One of the first mysteries to guide this journey was light itself. In ancient Greece, philosophers argued about how light behaved. Did it emanate from the eyes, reaching out like tendrils to touch the world? Or did it fall onto the eyes from objects carried on invisible currents? These early debates were more poetic than empirical, but they showed something essential. Even then, humans were trying to explain the strange, intuitive feeling of perception, how we see, and what it means for something to be real. Fast forward to the 17th century, and Isaac Newton proposed a theory of light based on particles, what he called corpuscles. This idea helped explain reflection and refraction, and aligned with his broader vision of a universe composed of matter and motion, where forces like gravity followed strict calculable laws. It made sense in a classical world, but the picture would soon fracture. In the early 1800s, Thomas Young performed an experiment that changed everything. He passed light through two narrow slits and saw something unexpected. Not just two bright patches, but a pattern of alternating light and dark bands. Interference, the kind that only waves produce. This wave model of light was further confirmed by James Clerk Maxwell, who in the 1860s unified electricity and magnetism into one elegant theory, showing that light was an electromagnetic wave travelling through space. For a time, the wave theory of light was complete, triumphant, and unquestioned. Then came the cracks. By the end of the 19th century, physicists encountered a problem that wouldn't go away. When they examined how metals emitted electrons under light exposure, a phenomenon known as the photoelectric effect, they found that brighter light didn't always mean more energy. Only light above a certain frequency could eject electrons, no matter how intense the beam was. This behaviour didn't make sense if light were only a wave. Energy in a wave should be spread out, gradual. But here, energy seemed to arrive in sudden bursts. Enter Albert Einstein. In 1905, he proposed a radical solution. Light wasn't just a wave, but also a particle. Specifically, he suggested that light came in discrete packets of energy, quanta, which we now call photons. Each photon carried a specific amount of energy, proportional to its frequency. If the energy was too low, it simply couldn't liberate an electron from the metal. This idea not only explained the photoelectric effect, but launched a new paradigm. Light could behave both as a wave and as a particle. This was the first real step into what would become quantum mechanics. But it raised more questions than it answered. If light could act like both a particle and a wave, could matter do the same? Louis de Broglie thought so. In 1924, he hypothesized that particles such as electrons could also have wave-like properties. This was soon confirmed in experiments showing that electrons could create interference patterns, something particles were never supposed to do. Matter, it turned out, could also be a wave. This duality of light and matter, of wave and particle, became one of the pillars of quantum theory. But even as this new view began to take shape, the world of physics was growing more complex, not less. In 1927, Werner Heisenberg introduced the uncertainty principle. He showed that you could not know both the position and the momentum of a particle with absolute precision at the same time. The more precisely you know one, the less precisely you can know the other. This wasn't a limitation of instruments. It was a fundamental feature of reality. Nature, at the smaller scales, was not precise and predictable. It was probabilistic, fluctuating, inherently uncertain. At the same time, Erwin Schrödinger was developing his famous equation, a mathematical tool that described particles not as points in space, but as wave functions, evolving clouds of probability that suggested where a particle might be found. Instead of tracking the exact path of an electron, you could now describe the likelihood of it being in a particular place at a particular time. From this emerged a radical new understanding of the universe. Particles didn't have fixed positions or velocities unless we measured them. Until then, they existed as probabilities, superpositions of all possible states. This shift was not merely mathematical, it was philosophical, and it divided the scientific community. Niels Bohr, Heisenberg, and others developed what became known as the Copenhagen interpretation, the idea that physical systems do not have definite properties until they are observed. Measurement caused the collapse of the wave function into a single outcome. Reality, in this view, was fundamentally dependent on observation. Albert Einstein was deeply skeptical of this. He believed that a theory which relied on randomness and observer-dependent outcomes was incomplete. God does not play dice with the universe, he famously said. He wanted a deeper, deterministic theory, one that would restore order beneath the surface chaos. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published the EPR paper, an argument meant to show that quantum mechanics was not a complete theory. They described a thought experiment involving two entangled particles. According to quantum theory, measuring one would instantaneously affect the state of the other, no matter how far apart they were. Einstein called this spooky action at a distance, and saw it as proof that there had to be hidden variables, unknown factors that would eventually restore causality and locality to physics. For decades, this remained an open question. But in the 1960s, physicist John Bell devised a way to test it. Bell's theorem showed that no theory of local hidden variables could reproduce all the predictions of quantum mechanics. Experiments soon followed, using entangled particles and clever setups to test the boundaries. The results? Quantum mechanics passed the test, again and again. Bell's inequality was violated. The correlations between entangled particles could not be explained by any local, hidden variable theory. Reality, as described by quantum mechanics, was non-local. Measurement on one particle could instantaneously influence the state of another, even at great distances. This was not just a victory for quantum physics, it was a profound shift in how we understand the fabric of reality. The old Newtonian view of a universe made of separate isolated parts gave way to a world of entanglement, superposition, and probabilistic outcomes. A universe that doesn't reveal itself fully unless we look, and even then, changes when we do. By the end of the 20th century, quantum mechanics had become one of the most accurate and successful scientific theories ever created. It could predict outcomes to astonishing precision, so precise that when scientists measured the magnetic moment of the electron, the theoretical prediction and experimental result matched to more than 10 decimal places. Yet, for all its success, quantum mechanics remains deeply mysterious. What is the wave function? Is it real, or just a tool for predicting probabilities? What exactly happens during measurement? Is collapse a physical process, or is it just our knowledge that changes? These questions remain open. Interpretations vary. Some physicists favour many worlds, in which every possible outcome happens in a branching multiverse. Others propose hidden variables or pilot wave theories. Some treat the wave function as entirely subjective, while others insist it describes something objectively real. And yet, quantum mechanics works. It underpins everything from semiconductors to lasers, from MRI machines to atomic clocks. It has given us technologies that shape the modern world, even as its foundations continue to provoke awe, debate, and wonder. It is a theory that has shown us a universe far stranger than we imagined, and more beautiful too. Not a machine, but a web. Not a certainty, but a song of possibilities. If the 20th century brought quantum theory into the world, then the late 20th and early 21st centuries saw it sharpened, stretched, and reimagined in ways its early founders could scarcely have predicted. The quantum revolution didn't stop with uncertainty or wave functions. It deepened into the very structure of matter, energy, space, and even information itself. One of the first major advancements came in the form of quantum electrodynamics, or QED. Developed in the mid-20th century by Richard Feynman, Julian Schwinger, and Zenitiro Tomonaga, QED was a quantum field theory that successfully described how light, photons, and matter, electrons and positrons, interact. It was an elegant synthesis of quantum mechanics and special relativity, and it introduced the world of virtual particles, probability amplitudes, and Feynman diagrams, a visual shorthand for particle interactions that remains foundational today. QED wasn't just a beautiful theory, it worked. Its predictions matched experiments with unmatched precision. The magnetic moment of the electron, for example, agreed with theoretical predictions to 12 decimal places. This level of accuracy made it one of the most successful theories in the history of science. From there, physics moved to unify more forces. Electroweak theory combined the electromagnetic force and the weak nuclear force into one framework, predicting the W and Z bosons, particles that were later discovered in high-energy experiments. These achievements formed the backbone of what became known as the Standard Model of Particle Physics, a theory that accounts for all known elementary particles and their interactions, except for gravity. It gave us a menagerie of quarks, leptons, bosons, and the famed Higgs boson, whose discovery in 2012 confirmed the mechanism by which particles acquire mass. But even as the Standard Model succeeded, it also left questions unresolved. Chief among them was gravity. Einstein's general theory of relativity describes gravity not as a force, but as the curvature of space-time. It works brilliantly on large scales, planets, stars, galaxies, but breaks down at the quantum level. Meanwhile, quantum mechanics rules the microscopic realm with astounding accuracy, but it has no place for curved space-time. The two theories, both foundational, speak different languages. Unifying them has become one of the great unfinished tasks in physics. One approach to this problem is string theory, which suggests that the fundamental building blocks of reality aren't particles at all, but tiny vibrating strings. These strings can resonate at different frequencies, giving rise to the particles we observe. The mathematics of string theory also requires additional dimensions, 10 or 11, depending on the version, which are thought to be compactified or hidden from our perception. String theory offers a promising framework that includes gravity and could, in principle, unify all the forces. But it also comes with challenges. Its predictions are difficult to test, and the theory allows for an enormous number of possible universes, which raises questions about its scientific falsifiability. An alternative approach, loop quantum gravity, attempts to quantize space-time itself. It replaces the smooth fabric of general relativity with a network of discrete loops, chunks of space and time that are quantized at the smallest scales. Like string theory, it's still speculative, but it's grounded in different assumptions and methods. It's another example of how quantum theory continues to generate not just answers, but entire new branches of inquiry. While these theoretical explorations continue, another profound shift occurred in the understanding of quantum mechanics itself, the rise of quantum information theory. Instead of asking what particles are or where they go, quantum information theory asks, what is information? How is it stored, transmitted, and transformed in a quantum system? It reimagines the quantum world not as a place of mysterious physical behavior, but as a system for processing data, a set of rules about how knowledge can change. This approach gave birth to fields like quantum cryptography, which uses principles like entanglement and no cloning to create secure communication channels. In these systems, any attempt to eavesdrop on a message introduces detectable changes, making the communication inherently secure. It also led to the concept of quantum teleportation, not the teleportation of matter, but of quantum states. In 1993, scientists showed that the exact state of a quantum particle could be transferred to another distant particle using entanglement and classical communication. This doesn't allow for faster-than-light travel or message transmission, but it does demonstrate something profound. The quantum identity of a system can be moved, even if the system itself remains stationary. And perhaps most notably, quantum information theory opened the door to quantum computing. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits, quantum bits that can exist in superpositions of 0 and 1. This allows them to process a vast number of possibilities simultaneously. When qubits become entangled, their states become linked in ways that allow for even more complex operations. Quantum computers are still in their early stages, but the progress has been swift. Companies and research institutions are now building machines with tens, even hundreds of qubits. The potential is enormous to simulate molecular interactions at a level classical computers can't reach, to solve optimization problems, to break encryption, or build entirely new kinds of security. Yet quantum computing also circles back to some of the foundational mysteries of the theory itself. It forces physicists to consider how information behaves at the quantum level, and whether quantum mechanics is ultimately about the structure of knowledge, not just matter. It reframes questions that once seemed philosophical. What is a measurement? What is reality? Into practical engineering problems. Meanwhile, new puzzles continue to emerge. One of the most famous is the black hole information paradox. According to Stephen Hawking, black holes emit radiation and can eventually evaporate. But if they do, what happens to the information about the matter that fell into them? According to quantum mechanics, information cannot be destroyed. Yet if black holes vanish entirely, where does that information go? This paradox has led to new ideas, including the holographic principle, which suggests that all the information contained in a volume of space might be encoded on its boundary like a hologram. This radical idea implies that the universe as we experience it may be a kind of projection from a deeper, more fundamental structure. It's speculative, but increasingly supported by research in string theory and quantum gravity. The idea that space-time itself might emerge from quantum entanglement, that geometry arises from information, is perhaps one of the most mind-bending developments in modern physics. It's a complete reversal of earlier thinking. Instead of particles and fields moving through a fixed background, the background itself may be built from the quantum connections between bits of information. And so, the journey continues. From early questions about light and shadow to deep theories of space, time, and information. Quantum physics has evolved not just as a branch of science, but as a new language for describing reality. Each generation has inherited questions, sharpened them, and passed along newer, sharper puzzles. Today, quantum theory touches everything, from the phones in our pockets to the edge of the observable universe. It informs our technologies, guides our experiments, and shapes our metaphors for understanding the world. And yet, for all its utility, it remains deeply strange. No other scientific theory has forced us to rethink so thoroughly what it means to know, to observe, to exist. The history of quantum physics is not a straight line but a spiral, one that keeps circling back to its core mysteries with new tools, new insights, and a growing sense of humility. It teaches us that progress is not about answers alone, but about asking better questions. That truth is not always found in certainty, but sometimes in openness. A century ago, Max Planck reluctantly proposed the idea of energy quanta to resolve a mathematical problem. He had no idea he was opening a door into an entirely new way of seeing the universe. Today, we still walk through that door, hesitantly, curiously, awake. And maybe that's the real legacy of quantum mechanics. Not just a theory, but an invitation to wonder, an invitation to listen, more closely than ever to the quiet, statistical, shimmering fabric of the world, and to discover, again and again, that it still has more to say. Quantum physics doesn't just change how we measure, it changes how we mean. At first glance, it's a theory about particles, energies, and probabilities, a mathematical toolkit that governs the tiny gears inside the universe. But the more deeply you follow its implications, the more the boundaries between physics and philosophy begin to dissolve. It stops being just a science and starts becoming something else. A mirror, maybe, or a metaphor. A way of understanding not just what reality is, but what it feels like to be inside it. Because quantum physics challenges more than our tools. It challenges our intuitions. It undermines the classical picture of a world that simply is, fixed, determined, observer-independent. Instead, it offers something more fragile and strange. A world that exists as potential, that becomes itself only when looked at, and only in a way shaped by the act of looking. This, in essence, is the philosophical heart of quantum mechanics. Take superposition, the idea that a quantum object doesn't sit in one state or another, but in a blur of possibilities, a smear across the probability landscape. It's not that the particle is at point A or point B and we just don't know which. It's that, before measurement, it's truly neither, or both. It is the potential to be either, and only when we observe does that potential resolve into a specific outcome. This is more than a mathematical quirk. It's a challenge to the notion that reality exists fully and concretely, even when no one's watching. It raises a haunting question. Does the world exist when we're not looking? The Copenhagen interpretation answers, gently but firmly, no, not exactly, not in the way you think. Measurement doesn't just reveal, it helps create. The observer is part of the system. That's a difficult pill to swallow. For centuries, science was about stepping back, removing bias, stripping away subjectivity to find something objective and universal. But quantum mechanics says that you cannot be entirely separate from the thing you study. There is no purely external view. In quantum mechanics, observation is not a window, it's an interaction. And suddenly, questions once left to poets and monks are being asked in physics labs. What does it mean to observe? What counts as a measurement? Where exactly does the boundary lie between the system and the observer? Some physicists say there's no such boundary, that reality is fundamentally relational, that properties, like position, spin, momentum, don't exist absolutely, but only in relation to something else. That's the heart of relational quantum mechanics, which suggests the universe isn't built from things, but from interactions, from perspectives, from context. This feels deeply foreign to our daily intuitions. We're used to thinking that things simply are, with or without us, that a chair is a chair, whether we see it or not. But quantum mechanics whispers, maybe not. Maybe a chair is a set of probabilities stabilized into chairness by your perception of it. Maybe the moon is there when you look, but not in quite the way you think when you're not. Of course, taken too literally, that becomes absurd. The moon doesn't vanish when we close our eyes, but the questions still echo. What is the relationship between our experience and the world? Where does reality begin? And what role do we play in shaping it? This is where quantum physics steps out of the lab and into the psyche, because there's something about its indeterminacy, its paradoxes, that maps oddly well onto our inner lives. Consider the Heisenberg uncertainty principle. It says that the more precisely you measure one aspect of a system, the less precisely you can know another. That sounds like a technical limitation, but it's also oddly human. Try to pin down your thoughts, and they scatter. Focus too tightly on your fears, and you lose sight of your joys. Try to capture a moment of pure experience, and it slips through your fingers. Attention changes what is being observed. The more you measure, the more you alter. Is this just metaphor? Yes, and also no. Quantum mechanics is not a theory of human experience, but it touches on the same paradoxes that shape our perception of life. It makes room for ambiguity, for uncertainty, for the idea that truth may be layered, not linear, that opposites can coexist, that outcomes are contingent. This brings us to perhaps the most famous thought experiment in quantum philosophy, Schrödinger's cat. Place a cat in a box, along with a mechanism triggered by the decay of a radioactive atom. If the atom decays, the mechanism releases poison, and the cat dies. If not, the cat lives. According to quantum mechanics, until we open the box, the atom is in a superposition of decayed and not decayed, and therefore, so is the cat, alive and dead, simultaneously. This was never meant to be taken literally. Schrödinger devised the scenario to illustrate how absurd the implications of quantum theory can seem when extended to the macroscopic world. But the image stuck, because it's haunting, and because it feels familiar. We've all lived in boxes of unknowing, waiting for a result, a diagnosis, a decision, trapped between outcomes that haven't yet collapsed, hoping, fearing, suspended in a liminal space. In that space, we are Schrödinger's cat. Neither outcome has happened, and yet, emotionally, both are real. We feel the weight of them before they arrive. We exist in the tension between them. Quantum mechanics gives us a language for that tension. It doesn't just describe particles, it describes the grammar of uncertainty, and from that grammar, whole philosophies emerge. Some interpretations of quantum theory, like the many worlds interpretation, take things even further. Instead of collapse, they propose that every possible outcome actually happens, just in different branches of the universe. The cat is both alive and dead, but in separate realities. The wave function never collapses, it simply forks. This is radical. It turns every decision into a divergence. Every quantum event becomes a point of branching. The universe is not a single unfolding narrative, but a vast, ever-multiplying tree of possibilities. If that's true, it raises profound existential questions. Are all versions of us equally real? Do we in some way live every possible life? Is free will an illusion, or does it mean choosing which branch we remember as ours? And if there are infinite versions of us, what matters most, the choice or the consciousness that experiences it? These aren't just academic questions. They bleed into how we live. Quantum mechanics doesn't tell us how to feel about uncertainty, but it validates it. It tells us that uncertainty isn't a failure of knowledge, it's a feature of reality. That ambiguity isn't something to eliminate, but something to embrace. That even the smallest particles of matter dwell in a kind of ontological openness. In this way, quantum physics becomes not just a science of the very small, but a philosophy of the in-between. It speaks to the spaces where things are not yet decided, where answers resist finality, where paradox is not a problem to be solved, but a truth to be held. That perhaps is why so many people feel drawn to it, even if they don't fully understand the equations. Quantum theory captures something about the shape of being alive. We live in a universe where observation matters, where possibility precedes outcome, where every interaction creates something new. Where what is true may depend, at least in part, on how you look. This doesn't mean that reality is just a projection of the mind. That way lies solipsism and confusion. But it does mean that consciousness is entangled with the cosmos in a way that's still not fully understood. Not because we're the center of the universe, but because we're part of it, and because the boundary between observer and observed is more porous than we imagined. For some, this feels spiritual. For others, it feels destabilizing. Either way, it's a call to pay attention, to acknowledge that reality is not simply handed to us, but shaped, at least in part, by our participation. We're not outside the system. We're in it. And perhaps that's the greatest philosophical gift quantum mechanics has to offer. Not certainty, but humility. Not control, but presence. In a world where things are always in flux, where outcomes are never fully predictable, where reality is both less and more than it seems, the invitation is simple. Stay curious. Stay open. Stay willing to dwell in the maybe. If quantum mechanics teaches humility, it also offers wonder, because the more deeply we explore the strange contours of the quantum world, the more it seems to echo age-old questions, ones that religions, myths, and philosophies have grappled with for centuries. What is the nature of reality? Is it continuous or discrete? Is there a fundamental unity behind appearances? Does consciousness shape the world or merely observe it? In many ways, quantum physics brings these ancient questions into new focus, not with dogma, but with data. It doesn't replace philosophy. It enriches it. Take the concept of entanglement. When two particles become entangled, their properties remain linked no matter how far apart they travel. Measure one, and you instantly know something about the other. Einstein called it spooky action at a distance, but it's since been confirmed countless times. There's no signal passing between the particles, no communication in the classical sense, and yet they act as if they're one system, even when separated by light years. To physicists, this is a fascinating quantum correlation. To philosophers, it raises deeper implications. Entanglement suggests that separateness may be an illusion, that the universe is, at some level, non-local and holistic. What happens here can have a meaning there, even without a visible bridge. And though this doesn't violate causality, entanglement can't be used to send signals faster than light. It challenges the classical idea of independent parts. The world is not made of isolated things. It's made of relationships. This resonates curiously with ideas from Eastern traditions. In certain schools of Buddhism, for example, the self is not seen as a static entity, but as a fluid network of causes and conditions. What we call a person is a temporary configuration of relationships, empty of fixed identity but full of interdependence. The same could be said of particles. An electron doesn't have a defined position until it's measured. A photon doesn't travel along one clear path. A particle's identity, in a sense, arises from its interactions, not from some intrinsic essence. Does this mean physics proves Buddhism, or vice versa? Of course not. Science and spirituality are different languages, but the resonance is there, and it suggests that quantum physics, far from being cold or mechanical, might actually offer a vision of reality that is open, interconnected, and even compassionate. Even the many worlds interpretation, bizarre as it may seem, carries philosophical weight. If every quantum event spawns a branching universe, then we're not just living one life, we're living all of them in parallel. Every decision you didn't make, every road not taken, is still taken somewhere. Somewhere, another you is walking the opposite path. This can be dizzying. But it also invites reflection. If all possibilities are real, why does this one feel so particular? Why do we experience only one timeline, one thread through the web of worlds? Some theorists argue that consciousness is what selects the path. Others say it's simply the nature of decoherence, that interactions with the environment cause quantum systems to behave classically. But the question remains open. Why this experience and not another? It's tempting to bring in metaphysical speculation here, to ask whether we, as observers, create the world or merely collapse it into being. But perhaps the deeper point is this. Quantum mechanics tells us that what exists is richer than what we see, that beneath the surface of ordinary life there's a sea of unactualized potential, and that might be the most profound existential message of all. Because we too live in superposition, not in the literal physical sense, but in the way our futures are not fixed, in the way our lives are shaped by probabilities, choices, observations, in the way we carry within us multiple selves, the person we are, the one we were, the one we might yet become. Quantum mechanics doesn't give us a script, it gives us a stage, a framework of possibility, a world where even the smallest moment contains a branching infinity. This isn't the same as saying anything is possible. There are rules, there are constraints, but within those limits, the play is wide open. That's what makes the quantum world so deeply human. It's not chaotic, it's probabilistic, structured but not sealed. And in that structure there's room for imagination. That's why quantum mechanics has long been a favourite playground for speculative fiction, science fantasy, and philosophical storytelling. It opens doors that classical physics kept closed. Time travel, parallel worlds, consciousness entangled across space, reality as simulation. These may not be scientifically proven ideas, but they are inspired by real physics, and they push us to think in new ways. They make us ask, what if? What if consciousness isn't an emergent property of matter, but a fundamental aspect of the universe, something woven into its quantum core? What if the brain is not just a biological machine, but a quantum computer, using coherence and entanglement to generate experience? There's little evidence for these claims, yet, but they're not nonsense. They're provocations. They ask us to reconsider the boundaries between science and mind, between physical law and lived experience, because ultimately quantum theory doesn't tell us what the world is. It tells us what we can say about it. It draws a map not of certainty, but of correlation, and in doing so, it challenges us to let go of old metaphors. The universe is not a clock, it's not a script, it's not a machine. If it is anything, it is a process, a flow, a tapestry of probabilities, constantly weaving and reweaving itself through observation, interaction, and time. In that sense, quantum mechanics is not just a description of particles, it is a philosophy of becoming, a reminder that what is depends on what could be, and that every act of looking is also an act of choosing. Maybe that's why the theory feels so strange, not because it defies logic, but because it requires a new kind of logic, a logic that can hold opposites, a logic that accepts mystery not as a gap in understanding, but as a part of the structure. Quantum mechanics doesn't answer every question. It leaves space for wonder, and in that space, we are free, not to know everything, but to imagine more than we knew was possible. Maybe that's what reality has been asking of us all along. Not certainty, but curiosity. Not dominance, but dialogue. Not control, but connection. Because to observe is not just to dissect. It is to participate, to witness, to wonder. And perhaps that's the truest lesson of all, that we are not separate from the universe. We are the universe looking at itself with trembling hands and blinking eyes, trying to make sense of the wave function before it collapses. Quantum physics often feels like a subject locked behind equations and particle accelerators, hidden in a realm too small to touch or too complex to grasp. But the truth is, the quantum world isn't out there. It's here, now. It shapes our everyday lives in ways both obvious and invisible, woven into the structure of reality, humming quietly beneath our routines, decisions, and technologies. In fact, you've already used quantum physics today. If you checked your phone, sent a text, or opened a laptop, you engage with systems that rely on quantum mechanics. Transistors, the tiny switches that form the backbone of all modern electronics, work because of quantum tunneling. Without it, microchips couldn't function. Semiconductor materials would behave like inert blocks, but quantum effects allow electrons to cross barriers they shouldn't be able to, letting electricity flow in carefully controlled patterns, bit by bit, logic gate by logic gate. Then there's GPS. The global positioning system depends on satellites equipped with atomic clocks, devices that rely on the energy levels of electrons within atoms, as defined by quantum transitions. Without quantum theory, those clocks wouldn't be accurate, and your map would be off by miles. Medical imaging too, MRI scanners, PET scans, all tap into quantum principles. The ability to see inside the body without cutting it open is a miracle made possible by the precise manipulation of spins, fields, and probabilities. But this is just the technical side. What's more fascinating, and less often discussed, is how quantum mechanics subtly influences how we think about ourselves, our choices, and our place in the world. Over the past century, quantum theory has slipped from the lab into the culture. Its ideas, metaphors, and paradoxes have filtered into literature, film, psychology, and popular imagination. It's become part of how we talk about mystery, possibility, and meaning. Take the phrase quantum leap. In physics, it refers to the discontinuous jump of an electron from one energy level to another, an inherently unpredictable, probabilistic shift. In culture, the phrase has come to mean a dramatic transformation, a moment of sudden change. We use it to describe breakthroughs, turning points, reinventions. The language of quantum mechanics becomes a language for growth. Then there's the notion of parallel worlds. The many worlds interpretation of quantum mechanics is still controversial, but it's become a staple of science fiction and speculative storytelling. Films like Everything Everywhere All at Once, Interstellar, and Spider-Man Into the Spider-Verse play with the idea that every decision spawns alternate realities, that somewhere another version of you is living the life you didn't choose. Whether or not this is scientifically true, it resonates emotionally. It gives us a way to think about regret, potential, and the branching paths of life. We imagine those other versions of ourselves not as ghosts, but as reflections. And in doing so, we acknowledge something quantum at the core of identity, that we are shaped by probabilities, by choices that narrow the field of outcomes, collapsing the possible into the actual. There's also a subtler influence, how quantum mechanics has softened our relationship with certainty. In a classical worldview, the universe is like a machine, predictable, logical, deterministic. You give it an input, you get an output. That idea shaped the modern world for centuries. But quantum physics challenged that narrative. It introduced a layer of unpredictability, not just from ignorance, but from the nature of things themselves. It showed us that even perfect knowledge of the present can't guarantee a precise future, and that shift ripples outward. Today, when we say that life is uncertain, or that we're learning to live with ambiguity, we're echoing the worldview that quantum mechanics helped popularize. It gave scientific weight to something deeply human, that not everything can be controlled or forecasted. That probability, not precision, might be the fundamental grammar of experience. This has psychological consequences. The rise of mindfulness, for instance, of learning to dwell in the present moment without grasping for outcomes, parallels the quantum idea that observation shapes reality. The moment of awareness is also the moment of transformation. In meditation, one learns to let go of certainty, to sit with paradox, to watch thoughts arise and fall like quantum states, unfolding, collapsing, moving on. And then there's emotion. People often describe feelings as quantum-like: love, grief, longing. These aren't linear processes. They're waves, probabilities, oscillations. You can feel two contradictory things at once. You can occupy emotional superpositions, joy and sadness, hope and fear. We don't live in binary states. We live in blends. In that sense, the emotional landscape of human life is profoundly quantum. Even our perception of time reflects quantum influence. Classical time is a steady march, tick by tick, second by second. But subjective time, emotional time, doesn't flow that way. It dilates when we're bored. It collapses when we're lost in thought. It reverses in memory. And in quantum mechanics, time isn't always straightforward either. Some interpretations treat it as emergent, not fundamental. Others propose that entanglement itself gives rise to time's arrow. So when we say that time flies, or that the moment stretched forever, we're not just using poetic metaphors, we're brushing up against truths that physics is still trying to explain. Culture picks up on these things. Quantum metaphors show up in art, poetry, even self-help books. There's something irresistible about the image of the world as uncertain, interconnected, layered with hidden patterns. It gives us a way to talk about what's hard to name. It comforts us too. Because if reality is probabilistic, then maybe we aren't stuck. Maybe possibility is always nearby. There's power in that. But it's also important to be careful. Not all uses of quantum theory in popular culture are accurate. Ideas like quantum healing or manifestation often misuse the language of physics to sell wishful thinking. The quantum world is strange, but it's not magical in the way some claim. Observation doesn't guarantee outcomes. Belief alone doesn't collapse the wave function of the universe into your ideal future. Still, the desire behind those interpretations, the longing to connect the personal and the cosmic, is understandable. Quantum mechanics doesn't tell us we control the universe, but it does suggest we're part of it more intimately than we thought. Not passive observers, but entangled participants. That idea, that we're embedded in the system, influencing it just by being here, is powerful. It changes how we see ourselves, not as separate from nature, but as part of its deepest rhythms, not as puppets of fate, but as collaborators in the unfolding of events. And maybe this too is quantum, because life is not a series of fixed states, it's a continuous dance of interaction. Every moment collapses the previous one and sets the stage for the next. We're constantly in motion, constantly observing, constantly changing the landscape just by moving through it. Quantum mechanics gives us a framework for that motion, not in the equations themselves, but in what they imply. That to live is to shape, that the future is not pre-written, that uncertainty is not a flaw, but a canvas. This reframes so many things. In relationships, it reminds us that people don't have single, fixed traits. Like particles, we reveal different aspects of ourselves in different contexts. We're never just one thing. We exist in relational fields, emerging through connection, not in isolation. In creativity, it reminds us that breakthroughs often come from superposition, holding contradictory ideas, allowing tension to build, and waiting for the moment when something clicks, when the waveform collapses into a new form. In decision-making, it tells us that there may be no perfect choice, only a narrowing of paths. Every step we take defines not just what happens, but what no longer can. And that's not paralysis, it's possibility. In aging, it helps us understand why time feels different as we grow. Memory, like measurement, creates the story. And as our story lengthens, the chapters compress, the earlier pages blur, and the present moment becomes more precious. Not because it's fleeting, but because it's rich with entanglement. Quantum mechanics doesn't explain the soul. It doesn't offer meaning in a spiritual sense, but it opens the door to a new kind of meaning. A meaning built not on permanence, but on participation. It asks us to pay attention, to notice the moment of collapse, the flicker of possibility as it becomes experience, to live with uncertainty, not as a threat, but as an invitation. Because if the world is quantum, then we are not separate from its strangeness. We are expressions of it, entangled, emergent, in motion, alive. Quantum mechanics might seem like the province of physicists and philosophers, but it has, over the last century, quietly seeped into the texture of how we live, how we think, speak, and interpret the world. It doesn't just show up in the electronics we use or the metaphors we borrow. It's reshaping our metaphysics, our psychology, and even our ethics. Take identity, for example. In the classical world, identity is simple. A is A. You are who you are. Stable, knowable, self-contained. But the quantum world doesn't work that way. Identity is relational, conditional. A particle might be an electron, but until it's measured, it doesn't have a fixed spin or position. Its state depends on context. Increasingly, we're beginning to see ourselves the same way. In the age of the internet, social media, and shifting roles, identity has become fluid. We are different versions of ourselves depending on where we are, who we're with, and how we're seen. Like quantum particles, we exist in overlapping roles and states: parent and artist, partner and stranger, observer and observed. We live in social superpositions, and while that may feel unstable at times, it's also freeing. The quantum perspective reminds us that multiplicity is natural. That contradiction is not always conflict. It can be coherence. Even the way we navigate knowledge has changed. In a deterministic universe, knowledge is something you uncover, a fixed truth waiting to be revealed. But in a quantum framework, knowledge is more participatory. You don't just find out what is, you influence what becomes. Your questions matter. The act of inquiry changes the outcome. That shift is reflected in how we learn, how we teach, how we think critically. We ask not just what is the right answer, but how does the way I frame this question shape what I'm likely to find? In science, this leads to more nuanced experimentation. In personal life, it opens space for emotional intelligence, for humility. Because quantum mechanics also makes room for the unknown. In a classical worldview, ignorance is a problem to be fixed, but in a quantum worldview, uncertainty is fundamental. There are things we cannot know, not because we're not clever enough, but because nature itself doesn't allow it. Reality isn't a locked vault, it's a shifting field. And that idea, unsettling as it might be, invites a gentler attitude toward the limits of our understanding. It teaches us that not every mystery needs solving. Some need witnessing. This has found its way into culture too, especially in how we tell stories. Think of films and novels that leave questions unanswered, that end with ambiguity, that invite the viewer to collapse the waveform in their own imagination. Quantum storytelling isn't about neat arcs or moral clarity, it's about multiplicity, possibility, uncertainty as aesthetic. Even our sense of space is changing. Classically, the world is made of things in places, but quantum physics says space is not just an empty container. It may be emergent, it may be constructed from networks of entanglement, from information itself. What if space is not fundamental, but derivative? What if distance is not always what it seems? This perspective resonates with our increasingly digital lives. Online, we communicate across vast distances with no real sense of separation. We connect to ideas, communities, and experiences in ways that defy geography. In a strange way, the internet has made the world feel more quantum, entangled, networked, non-local. Quantum physics has also influenced how we understand ethics and responsibility. In a deterministic universe, every event has a cause, everything is traceable. But in a probabilistic universe, cause and effect become less direct. Outcomes are not always the result of intentions. This raises subtle questions. If the world is governed by chance, where does responsibility begin and end? This doesn't mean morality disappears, but it does mean we may need to think about it differently. In a quantum universe, small actions can have disproportionate effects. A measurement here can ripple across entangled systems. That idea maps neatly onto human life. A word, a gesture, a decision, each can collapse a world of potential into one lived path. We may not control outcomes, but we influence probabilities. We shape what's likely. This invites an ethic of attentiveness, of mindfulness. Not because we're in charge of everything, but because everything is delicately, subtly responsive. Quantum theory also has emotional consequences. It provides a vocabulary for hope. In a classical world, things either happen or they don't. If a door is closed, it stays closed. But in a quantum world, nothing is final until it's observed. Possibilities linger. They remain in play. The future is not a narrowing tunnel. It's a shimmering cloud. This doesn't mean anything can happen, but it does mean we don't always know what will. There is room for surprise, for the unexpected, for the unlikely miracle. The wave function, until measured, keeps dreaming. You see this in how people speak about transformation, about redemption, about waiting for a new version of life to emerge. Quantum metaphors give emotional weight to the idea that we can remain open to what hasn't happened yet. They also help explain resilience. When something falls apart, a job, a relationship, a plan, we often feel like a waveform has collapsed into the worst possible outcome. But quantum thinking reminds us that collapse isn't the end. It's a transition, from potential to new potential, from one set of probabilities to another. There's always another measurement, another moment, another chance to re-entangle with possibility. This kind of thinking is showing up in therapy too. Psychologists draw on quantum language to describe states of inner conflict or change. They speak of clients living in emotional superposition, holding grief and relief, fear and courage, love and anger all at once. They speak of therapeutic breakthroughs as moments when old patterns collapse and new selves emerge, moments of quantum transition. Again, these are metaphors, but they're useful ones, because they reflect a deeper truth, that we are not fixed objects, we are processes, fields of probability shaped by history, perception, and attention. Quantum mechanics doesn't solve the human condition, but it frames it more honestly. It tells us that complexity is not a flaw, that contradiction is not failure, that we are not alone in our uncertainty. The universe too is figuring itself out, moment by moment, measurement by measurement. And then there's beauty. The strange, haunting beauty of the quantum world has inspired artists of all kinds. Musicians write compositions based on uncertainty and entanglement. Painters explore the visual analogues of superposition. Poets describe the feeling of being both here and not here, like particles in dual states. These works don't explain quantum mechanics, but they evoke it. They create emotional analogues to mathematical truths, and in doing so, they help us feel what we can't quite understand. Because that's what art does. It takes the inexpressible and gives it form. And maybe in that way it's closer to quantum reality than we realize. Because in the quantum world too, form arises from interaction. Meaning emerges from relationship. There is no single answer, only waves collapsing again and again into the moments we call real. In our everyday lives, we rarely think about this. We go to work, cook dinner, sit in traffic, make plans. But underneath it all, the quantum world persists. Every atom in your body obeys its rules. Every nerve impulse, every glimmer of thought is shaped by fields and particles in uncertain motion. We are quite literally made of quantum stuff, and that's not metaphor, that's fact. But what we make of that fact, that's up to us. We can ignore it, we can romanticize it, or we can live with it, quietly aware that the world is more fragile and flexible than it seems, that nothing is quite as solid as we pretend. That possibility is not a luxury, it's a condition. To live quantumly is not to reject logic, it's to embrace a fuller logic, one that includes the unknown, the interactive, the emergent. It means letting go of rigid narratives. It means accepting that your life doesn't have a single storyline. It means knowing that you too are a superposition of hopes and fears, of memories and dreams, of particles and probabilities, and that is not weakness, that is wonder. Quantum mechanics is strange enough as it stands. Uncertainty, superposition, entanglement, particles that behave like waves. But if you lean just a little further into its implications, something remarkable happens. It begins to look like science fiction. Not because it's fake or fantastical, but because it challenges the very rules of what seems possible. And from that edge, where science and imagination meet, some of the most enduring what-ifs in physics begin to unfold. What if we could travel in time? What if there are infinite versions of ourselves playing out every possible future? What if the world we live in is just one realization in a sea of quantum outcomes? These aren't just stories, they're thought experiments, some born in the minds of theoretical physicists, others in the pages of novels or the frames of films. But all of them have roots, however tenuous, in real scientific ideas. Start with time travel. In classical physics, time is absolute. It moves forward, steadily, like a metronome. But Einstein's relativity already loosened that idea. Time could stretch or contract depending on your speed or gravitational field. Travel close to the speed of light, and time slows for you relative to others. Enter a region of extreme gravity, say, near a black hole, and time can nearly stop. Quantum mechanics adds another layer. It treats time less as a universal flow and more as a parameter in an equation. Some interpretations even suggest that time itself might emerge from entanglement, or from changes in information. In other words, time may not be a basic ingredient of the universe, it might be a side effect of quantum processes. And once you loosen time from its pedestal, the questions come quickly. Could we reverse time? Could particles go backward? Could a quantum system remember the future? Physicists have explored this. Certain equations in quantum theory are time-symmetric. They work the same whether time moves forward or back. That doesn't mean we can reverse time in practice, but it opens the door to paradoxes. One of the most famous is the quantum grandfather paradox. Imagine sending a particle back in time, where it interferes with its own past. In classical logic, this creates contradiction. But in quantum logic, where outcomes are governed by probability, the situation becomes fuzzier. Maybe the particle exists in a superposition of having changed the past and not. Maybe the timeline splits. Maybe the paradox just becomes part of the whole. This kind of reasoning is what gives rise to the many worlds interpretation. According to this view, every quantum event that could happen does happen, just not in the same universe. Instead, the universe branches at every decision point. Measure a particle's spin, and the world splits into two, one where it's up, one where it's down. Choose left instead of right, and somewhere else, you chose right. In this model, the universe is constantly forking into new versions of itself. You're not a single thread. You're a branching structure of possibilities, and the consequences of that idea are staggering. Because if many worlds is correct, then right now there are countless versions of you reading this sentence. Some paused, some skimmed, some stopped reading halfway, and all of them are real, just inaccessible from one another. It's not science fiction, it's math. That's what makes it so haunting. Unlike traditional sci-fi, which requires suspended disbelief, quantum interpretations like many worlds emerge directly from the mathematics of the theory, just without the assumption that the wave function collapses. In this view, there's no need for a mysterious measurement to force a single outcome. All outcomes happen. You just happen to live in the one you're aware of. This opens up the possibility of parallel worlds, not in the comic book sense, with portals and duplicates, but as a natural consequence of quantum evolution. It also changes how we think about fate and free will. If all possible futures already exist, then choosing isn't about eliminating options. It's about discovering which path you're living in. That's both liberating and terrifying. And yet, even more speculative ideas follow. One of the most intriguing is quantum immortality, a thought experiment. Not a proven theory, but a consequence of taking many worlds seriously. Imagine a scenario in which your survival depends on a quantum event, say, whether a particle decays or not. In some branches of the universe, you die. In others, you survive. From your own point of view, the one doing the experiencing, you would always find yourself in the surviving branch. No matter how many risks you take, there's always at least one branch where you make it through. In theory, that leads to a strange idea, that you might experience survival in every case where it's physically possible. That from the inside, consciousness continues indefinitely, always finding itself in the version of events where it didn't end. Again, this isn't a claim that anyone lives forever. It's a logical consequence of merging quantum indeterminacy with subjective experience. It's strange, it's disturbing. But it emerges naturally from the same rules that govern double-slit experiments and Schrödinger's cat. And speaking of Schrödinger's cat, perhaps the most enduring quantum paradox of all, it too belongs here. The image is simple. A cat sealed in a box, its fate tied to a quantum event. Until observed, it exists in a superposition of alive and dead. A paradox meant to challenge the Copenhagen interpretation, but also one that captured the imagination of generations. And what it reveals is this: that quantum theory isn't content to stay small. Its strangeness scales up. It doesn't just apply to electrons and atoms. It asks us to consider what happens when we become part of the experiment. This idea has spawned endless fiction. Films where decisions split timelines, characters who remember futures that haven't happened, worlds where reality shifts because someone changed their mind. But the fiction is always circling the same core question: what is real? In classical physics, that answer is simple. What happens, happens. But in quantum physics, it's more delicate. Reality isn't a fixed script, it's a stage set for countless possible performances, and we, somehow, are both actors and audience. This makes quantum mechanics the perfect substrate for imaginative exploration. It's no accident that popular culture has embraced quantum themes: multiverses, entanglement, time loops, quantum consciousness. The language of physics becomes the language of story, of dream, of inner life. Because these aren't just science problems, they're existential ones. What if your choices really do echo across alternate versions of the world? What if the self is not a singular thing, but a network of possibilities? What if death is a change of state, not an end, but a divergence? These are the kinds of questions people once asked in temples and monasteries. Now we ask them in labs and lecture halls, armed with lasers and equations, but the wonder remains the same. Quantum physics doesn't prove these ideas, but it allows them. It creates space within the structure of science for things we once thought belonged only to imagination. And that's why, perhaps, quantum theory feels so poetic, because it brings us back to mystery, not in opposition to science, but as its natural conclusion. The deeper we look into the workings of matter, the more the line blurs between fact and interpretation, between what is and what could be. It invites us not just to calculate, but to contemplate, to wonder what else might be true, if only we look closely enough. If quantum mechanics has taught us anything, it's that the boundaries between what's real and what's imaginable aren't always clear. The equations work, the predictions hold, and yet the interpretation, the meaning, remains open-ended. That openness, that refusal to settle into certainty, creates a space where science and story coexist. It also creates paradox, and quantum theory is full of them. Take the delayed choice experiment. First proposed by John Archibald Wheeler, it's an elegant twist on the double-slit setup. A photon passes through a pair of slits and then hits a detector. But just before it's detected, we choose whether or not to erase the which path information. And strangely, this choice seems to affect whether the photon behaved like a wave or a particle, after it already passed through the slits. In other words, our present decision seems to influence the particle's past behaviour. It's not quite time travel, but it suggests that the line between cause and effect isn't as solid as we thought. That perhaps reality doesn't have a definite history until it's observed. That maybe somehow the future helps shape the past. This kind of retrocausality isn't widely accepted, but it isn't ruled out either. And in quantum theory, not ruled out is often just a few decades ahead of proven true. It also highlights something essential. In quantum mechanics, observation doesn't just reveal, it defines. And that's what leads so many to speculate about consciousness. Could the mind itself be entangled with reality? Could awareness be what collapses the wave function, not just of particles, but of experience itself? Some physicists, like Eugene Wigner, seriously considered this. Others, like Roger Penrose, have explored whether consciousness might arise from quantum processes in the brain. The idea is controversial, difficult to test, easy to abuse, but it's not inherently absurd. It simply asks, what happens when the observer is also a quantum system? If consciousness plays a role in shaping outcomes, then subjectivity isn't a byproduct of the universe, it's part of its architecture. This would change everything, because it would mean that consciousness is not just a candle flickering in the dark, it's one of the forces that sculpts the dark itself. That's a huge claim, and one that, so far, remains speculative. But even without leaping to grand metaphysics, we can still ask quieter questions. What if awareness isn't something that happens in the brain, but something that interacts with the world? What if each moment of attention is a kind of quantum selection, a narrowing of the possible into the actual? In daily life, we already act as if this is true. We focus, we choose, we watch. And in doing so, things become real to us, not always in the world's eyes, but in our own. What we observe grows sharper. What we ignore fades. That sounds a lot like wave function collapse, and while this may be poetic more than literal, it shows how quantum ideas echo in our psyche. It's not just about particles, it's about presence. The observer effect isn't just a lab phenomenon, it happens in conversation, in relationships, in emotion. We affect what we observe. Our attention changes the outcome. That's a quantum truth, and a human one. Which brings us back to the paradox of being. In a universe of infinite possibilities, how do we live a single life? Quantum theory tells us that all outcomes exist, somewhere, but we don't experience all of them. We walk one path, we make one choice, and with each collapse something is gained, and something is lost. The weight of that choice is both terrifying and beautiful, because if every version of reality is possible, then the one we live in matters because we're living it, because it's the one we experience, remember, feel, and because we know, consciously or not, that it could have been otherwise. That awareness is where ethics enters the picture again. In a classical world, morality is about rules. cause and effect, action and consequence. But in a quantum world, things are less rigid. There's fuzziness, overlap, complexity. We don't always know what effect we'll have. We can't see the full web of entanglement our actions touch. So we proceed more gently, with more attention, with an ethic of uncertainty. Because in the quantum world, even small choices ripple. A single observation can reshape the system. A single intention can shift the probabilities. That's not magic. It's how the math works. And once you realize that, you begin to live differently. You listen more. You measure less aggressively. You become comfortable not knowing. You start to see the universe not as a machine, but as a conversation. Not as a blueprint, but as a field of emergence. And you begin to suspect that the deepest truths might not be about prediction or control, but about connection. Which brings us to the sci-fi part again. Because quantum theory is fertile ground for stories of entanglement, not just between particles, but between people, places, timelines. Imagine a world where communication happens instantly across light years, not by sending signals, but by manipulating entangled states. Theoretically, it shouldn't work. Quantum mechanics forbids faster-than-light messaging, but people keep imagining it anyway, because it feels like it could be true. Like entanglement is a thread we haven't fully unraveled. Or imagine using quantum coherence to build consciousness beyond biology. AI systems that dream in probabilities, that think in wave functions instead of logic gates. Would they experience time the way we do? Would they have selves? Would they collapse their own realities? Or consider quantum teleportation, already demonstrated in labs, not for people, but for particles? It works by transferring quantum states from one place to another using entanglement and classical communication. Could something like that one day scale? Could we send ourselves across space? Not by moving mass, but by transmitting information. These ideas border on science fiction, but they begin in science fact. That's the beauty of the quantum world. It doesn't close doors, it opens them, and it reminds us that mystery is not a problem to be solved. It's a condition to be lived with, because the most profound quantum paradox isn't technical, it's existential. We live in a universe where certainty is impossible, where the future is a cloud, where every action is both limited and limitless, where observation creates reality, and yet we never quite know what we've created until it's already happened. We are not gods, we are not puppets, we are something in between. Agents of uncertainty, architects of maybe. That's the essence of the quantum what if. What if this is all there is? What if this is only one of many? What if the thing we call reality is just the collapse of possibility, flickering one frame at a time under the gaze of something watching? And what if the watcher is us? Not just individually but collectively, not just consciously but cosmically. What if the universe is not a stage, but a mirror? Quantum physics doesn't answer these questions, but it lets us ask them, not with fear, but with fascination. It invites us to imagine, not because we lack knowledge, but because knowledge itself is incomplete. And so we dream, and so we wonder. And in that wonder, something shifts. Possibility narrows, probability resolves, and the wave function quietly collapses into now. So where does all of this leave us? After diving through particles and paradoxes, through slit experiments and branching timelines, we emerge not with a final answer, but with a deeper, softer question. How do we live in a universe where certainty is an illusion, and possibility is the rule? Quantum physics, for all its complexity, doesn't seek to control the universe. It seeks to describe it. And what it describes is not a machine, but a rhythm, a pattern, a probability field that trembles with potential and only becomes concrete when we pay attention. There's no master plan, no rigid path, just wave functions unfolding into the moments we call now. We began with the idea that nothing makes sense, and yet everything works. And perhaps that's the most honest summary of quantum reality. It defies common sense. It challenges our instincts about space, time, identity, and cause. But despite all of that, it works with breathtaking precision. Our phones, our GPS, our medical technology, our understanding of the cosmos, all of them depend on these invisible, probabilistic rules that no one fully understands. Reality, it seems, does not need to be intuitive to be true, and yet the intuition's quantum theory evokes, the metaphors it inspires, are strangely human. It speaks of entanglement, and we think of love and connection. It speaks of uncertainty, and we think of choice and chance. It shows us that the world is not built from things, but from interactions, and suddenly we see ourselves not as isolated minds, but as participants in a vast and ongoing conversation. Maybe that's the real message, that what is real isn't a list of facts, but a process of engagement, that what exists depends on how we look, and that the act of looking, of truly being present, is creative, not passive. We aren't just watching the universe unfold, we're helping shape the way it unfolds, moment by moment. In this light, the quantum world becomes less of a puzzle and more of a poem, one where the lines don't always rhyme, but the rhythm carries a strange and sacred coherence, one where meaning isn't imposed from above, but emerges from connection, attention, and context. So maybe the universe is not a clock, or a computer, or even a vast equation. Maybe it's more like a mirror, one that reflects not just what is, but what could be, depending on how we hold the light. And maybe we too are mirrors, fragile, flickering surfaces through which the cosmos comes to know itself, not completely, not finally, but intimately. Quantum physics does not provide closure. It invites awe. It reminds us that truth can be partial, beauty can be strange, and uncertainty is not the enemy of meaning. It is the ground from which meaning grows. So if you're still wondering how to live with all this, how to walk through a world made of shimmering maybes, the answer might be simple. Live gently, choose with care, notice the moment, honour the unknown, and remember that even in the smallest action, the quietest glance, the most fleeting feeling, something is always collapsing into being. And that collapse, that moment of becoming, is not just science, it is life. So, where are you now? What time is it? Not on the clock, but in your life, in your thoughts, in your body. Is it night where you are? Quiet, still, and soft around the edges? Or are you somewhere in the folds between moments, that quiet liminal space where sleep begins to pull you inward? Wherever you are, thank you for being here, for drifting with us through the strangeness, the wonder, and the gentle uncertainty of the quantum world. If this brought you a moment of calm, or helped you see the universe in a new light, I hope you'll consider staying with us. You can subscribe, leave a thought, or simply carry the feeling with you as you rest. Remember, you're not separate from the fabric of the cosmos. You're entangled with it, a node in the great unfolding pattern. Every breath you take, every thought that flickers behind closed eyes, is part of the same vast story. So breathe easy. Let the wave function of your day collapse into stillness. And if your mind wanders, let it. If your dreams stretch out like probabilities, welcome them. There is no need to solve everything now. Let the questions linger like stars at the edge of vision. Sleep well, fellow traveller, wherever and whenever you are.